So the final section we are going to be looking at here in chapter 7 on similarity is called parts of similar triangles. So we're kind of uniting a couple of concepts here from earlier in both the unit and in our work in geometry. One is that we're going to be applying some of the proportionality that we talked about with side lengths in similar triangles, but also talking about some of the segments that we talked about earlier in the year when we were working through our, say, points of concurrency in triangles, when we were talking about where the medians and the altitudes and the angle bisectors and the perpendicular bisectors meet in a triangle. And so that incenter, circumcenter, orthocenter, centroid points of concurrency. So recall some of those ideas from earlier in the year. All right, so we can apply that same ideas for those special segments in similar triangles. So the first one that we have here, notice, is an altitude. Recall that an altitude goes from a vertex of a triangle and is perpendicular to the opposite side. So we have altitudes in these two triangles. And so if two triangles are similar, the lengths of the corresponding altitudes are proportional. Right, so I'm just going to write kind of that if-then statement below here just to clarify. So if triangle ABC is similar to triangle FGH, then we're going to compare our altitudes. So I just outlined our altitudes, AD and FJ, and that will have the same ratio as a side length. So let's just pick a side length. Let's say AB is a side length in that first triangle, and then the corresponding side length in the second triangle would be FG. So that same relationship would be true for our other side length as well. So if we wanted to talk about the corresponding ratio here, or even the ratio for the bottom segment, that same rule would apply. The altitudes, when we compare those two lengths, would be in proportion to the other side lengths. So let's just put some numbers on here just for clarity. So let's say this altitude AD was 6, and let's say altitude FG was 3. Then that's a 2-to-1 ratio or a 1-to-2 ratio, depending on which direction you were going. So let's say AB is 8, that would mean that FG would have to be 4, so it would also be in that 2-to-1 ratio. All right, so in the second diagram, notice that we have another one of our special segments. In this case, we are looking at our angle bisectors. Recall an angle bisector is a segment that splits an angle into two congruent parts. So LP splits angle L into two congruent parts, and RT is an angle bisector that splits angle R into two congruent parts. So that same relationship that we talked about with our altitudes is going to apply here. So I'm not going to write the whole if-then statement again, but I am going to put some numbers on here just to clarify. So if we said that we have 6, or maybe I should be a little bit more clever with this, or a little bit different. Well, let's say 6/2 this time. So 6/2 is a 3-to-1 ratio. And so therefore that same ratio would apply here. So if this was 9, then this would have to be 3, right? So that 3-to-1 ratio. So again, 6/2 would be the same as 9/3, right? So I'm just going to write that up here too. So 6/3 was equal to 8/4 when comparing the altitudes, and now we're comparing the angle bisectors, and we see they are in the same proportion. And then the third of our special segments that we're going to talk about here is a median. So recall that a median goes from a vertex to the midpoint of the opposite side. Notice this is a midpoint because we have congruent markings here and here. And then this is also a median, although I think I disagree with the way the markings are here. I think we really need to have two congruent markings on this one, because although ZW is congruent to ZX, it's different than our first triangle, BD and AD. So I'm going to make that adjustment here. And so if two triangles are similar, then the lengths of the corresponding medians are proportional to the lengths of the corresponding sides. So in case we want to put numbers on here, we certainly can. Whoops, let's try that. So we have, 10, and let's make this, let's make it 5. Not being very original, but oh well. 2-to-1 ratio there. I am kind of an amateur at this right now with our, keep hitting that plus button on the bottom of the page. Apologize for that. So that's a 2-to-1 ratio. And so if we were going to look at, say, even this dB right here, let's say that's 2, and let's say Zx is 1, which of course means that AD would have to be 2, and WZ would have to be 1. So there's a 2-to-1 ratio between the 2 and the 1, but also notice there's a 2-to-1 ratio with the whole side length. So that's whole side length is 4, and this whole side length is 2. So there's that same 2-to-1 ratio there, as was true with our medians. Now let's go down and try out an example. So notice in example number 1, we're told that we have two similar triangles, and therefore these segments will also be proportional. And in this one, notice we're looking at angle bisectors. And the angle bisectors, when we compare them, so if we compare A to P here, that is going to be a length x, and that same angle bisector over here, FQ, is going to be 8. So x over 8, and then we're going to compare a side length that we're given here. So this side length right here is going to be 15. And this side length over here, that corresponding side length, will be 12. All right, so now we're going to solve the proportion just like we have done throughout the unit. Again, I kind of like to use my cross multiply and divide. I know not everyone thinks that's the best method, but I'm going to continue to use it. It's easy. So 12 times x is equal to 8 times 15. So that would be 12x is equal to 120. And then dividing both sides by 12, x is equal to 10. We are being asked to find the value of x, so that is exactly what we did find. And so therefore the angle bisector is going to be 10 in that first triangle. Now notice in the next theorem here that it's just a little bit different than the other ones, because now we're just working with one triangle instead of comparing two triangles together. So that one triangle, notice we have some coloring in there to kind of help outline this. So what we're going to say here is that an angle bisector in a triangle separates the opposite side into two segments that are proportional to the lengths of the other two sides. All right, so what do we mean by that? Well, here we have an angle bisector. Notice that the markings are there for an angle bisector. And we're looking at and putting some numbers on here. So let's say this side over here is 8. And that segment there, KM, which is the segment created by the angle bisector, is 4. So notice there's an 8 to 4 or 2-to-1 ratio. So what we're saying is that this other side down on the bottom, JL, if that is 6, then the other side of the segment that is created by that angle bisector would have to follow that same 2-to-1 ratio. So that would have to be 3. So 8 over 4 is equal to 6 over 3. So notice we're actually not talking about the length of the angle bisector itself. What we're saying is that the angle bisector splits the opposite side into proportional parts when we compare it to the corresponding side lengths, 8 and 6. Okay, so let's go ahead and do an example related to that on the next page here. All right, so find x. Oh, there it is, found it. So we have these side lengths here of 14 and 6. Here's our angle bisector. And therefore it splits that opposite side into proportional parts with the 6 and the 14. All right, notice that we're given something a little bit different though here. We're given the entire side length, QS is 18. And so we know QT is x. And think about how we would express TS then. How would we express that side length? Because we really do need this ratio. Remember, we're looking at, and use a different color here, we're really looking at these two together and how they match up with these two together. And so if we look at that, we'll notice that in this problem, we could express this side length over here as 18 minus x. In other words, if x was, say, 5, then 18 minus 5 would be 13. Right? 5 plus 13 gives us our total of 18. So that's the best way to express that. Now let's put our ratio together. So what we're saying is, let's look at 6 over 14 is going to be equal to x over 18 minus x. And by the way, you could have set this up in a few different ways, actually corresponding with what I had said on the previous page. You could also set up your ratio as like 6 over x, and look at just the red segments, is equal to 14 over 18 minus x, which would have been those green segments. So you could actually work that out and notice that we can have that the same proportions will apply there as well. All right, so I'm gonna go ahead and solve this first one. So again, cross multiply and divide. That's how I like to solve my proportions. So here we've got our 14x is going to be equal to 6 times 18 minus x. So 14x is equal to, use the distributive property here, 108 minus 6x. All right, now let's just do our algebra correctly here. Let's get these x's onto the same side of the equation, undo it from the right side and add it over to the left side. And that leaves us with 20x is equal to 108. And then to undo 20 times x, to undo the 20, undo multiplication, we will divide. And so we have x is equal to 5.4. So that is our length of x, and then, so that's QT, by the way. And so if you were looking for TS, it doesn't ask us for that, but then you could just take 18 minus 5.4, which would be what, 12.6, if you wanted that side length. Now, if you solved the proportion over here, notice we would end up with the same situation because you'd have 14x is equal to 6 times 18 minus x. So we end up with the same answer.